Let me introduce Ping Fu.
Well, thank you, Joe. That's quite a support. I'm very excited to introduce Alexander Rose, who is Executive Director of Langnau Foundation, of which I am a board member. And Zander is someone that I totally admire. And if you think I am a jack of all trades, that I did a lot of things, he is amazing. And I recommend you to go to langnau.org site and look up his bio. I'm just going to mention a few. Zander started as an artist. He was artist at residence at Silicon Graphics a long time ago. He also co-founded a robotic company. His combat robot won 6 world champions in the TV show BattleBots, if you have ever seen that. And he's like world champion for Iron Man. It goes on. You just have to go onto the side to see what he does. But I don't want to go very long into the introduction because I want you to listen to Zander rather than me. I just want to say I dearly love him and totally admire him. And then if you love his talk and if you love what Langnau Foundation do, I do recommend you to become a member of it. The membership is very inexpensive. What you're getting from it is incredible. And also, Langnau Foundation is building a conversation bar at their museum in San Francisco. And it's just a fabulous place. And I encourage you to talk to Zander and maybe also help us to build it. It's a great place for conversation, innovation, invention, and it's also a great way to ensure the longevity of the Langnau Foundation. Thank you. Without overdue, ladies and gentlemen, Zander Rose.
Thank you, Ping, and thank you, Brad and Joel, for having me here and working with me before this talk as well. This is my first time here, but as you heard, I've had a little bit of background in 3D modeling and software industry that came to it mostly from a design perspective, and it wasn't started back with doing industrial design largely, and strangely found myself in a situation where I was designing something that had to last for 10,000 years. The origin of this project really was with a story that, that Stuart Brand told to a computer scientist, Danny Hillis. And that story was of the beams at New College, Oxford. And at least parts of the story are true, but it's such a great allegory, I keep telling it. But the beams over the main hall there were made of very large oak trees. And the New College at Oxford was new back in the 1200s. But 500 years later, in the 1800s, these beams had become a bit rotted and infested with beetles. And they didn't quite know what to do because you couldn't just go buy oak trees like this in Europe and go to the lumber yard and replace them. And so it wasn't until they spoke to the school forester who said, oh, well, we have the trees that you planted. And it turned out that when they built the school, they also planted a grove of oaks to be harvested 500 years later to replace this. And when Stuart told this to Danny, so Stuart had started the Whole Earth catalog. He had been kind of a culture hacker from the beginning. Danny Hillis was a computer scientist. He had been designing some of the fastest computers in the world. Danny realized that in building the fastest computers in the world, there was a large space that was being ignored, which was the space of things that need to take a long time and that culture needs to pay attention to over a long time. If it's going to be something like solving world hunger or climate change. There's no way you're going to do that if you are only taking a 4-year election horizon or a 5-year company plan. You need to be thinking generationally in order to solve some of these problems. And unless you're thinking generationally, you're not even going to start to solve some of these problems. So the thought was that we should do a project that is inspiring on these timescales. And Danny Hillis, being an engineer, thought, well, we should build a clock. And it should keep track of time on a millennial timescale. And Stuart Brand thought, well, that's great, but if we get people's attention on that timescale, we should also build a library or information service that kind of keeps information for culture over the same kind of time span. And one of the other people who got involved early on was Brian Eno, who's an artist and musician who you may know. And he coined this term, the long now. And it was when he moved from England to the United States. He realized that especially New York, when they said now, they meant the 5 minutes that we are in, as opposed to England, where he'd come from, where they meant the kind of time that we are in. And many other people, including Esther Dyson, who's going to be speaking here tomorrow, were part of the founding board, and then Ping is one of our newest board members, who I met as part of the clock project. And so I'm going to tell you about building this clock. I'm also going to tell you, but I'm going to start with kind of lessons in robustness and resiliency and things that have lasted over 1,000 years that have been inspirations for our project, and kind of why they have lasted and why we still have them, or in some cases, maybe why we don't. And I just wanted to mention a little bit about what our timescale really is. Our timescale should not be, in a human scale project, should not be on the order of billions of years in astronomical timescales. It kind of dwarfs that human experience. Even the kind of millions of years in geology really dwarfs that experience. There's not much you can do if you are trying to affect things on the millions of year scale. But this idea of 10,000 years is really the kind of human moment. The last ice age receded about 10,000 years ago. Agriculture started, and this is about as long as we've had technology. So the thought was that the Long Now Foundation would take responsibility and put in context the last 10,000 years, as well as the next 10,000 years, assuming we're basically in the middle of that story. And the way we would put some of that in context would be to try a kind of ridiculous and audacious project of building a giant mechanical 10,000-year clock. And it would be a thing that people could come visit, get inspired, have different conversations. So you're probably going to walk away from this talk wondering why you came to this talk. I'm hoping that that's the case, and I'm hoping that the reasons for this talk kind of seep into your consciousness slowly as you refer to possibly some of the other things that have lasted for a very long time, and hopefully that idea of resiliency starts to make sense in a different way than it might before. So first, I do want to talk a little bit about resiliency and some of the ways that nature has done it. One of the first places that we actually purchased to build the 10,000-year clock was a site in eastern Nevada that has these bristlecone pines on it. And some of these trees have been dated to over 4,800 years old. They're some of the oldest living organisms in the world. And the interesting thing about these trees is that they were actually predicted before they were discovered. A person wrote a paper called Adversity Breeds Longevity, and he had been coring pine trees, and he realized that the pine trees that were living in the worst environments were the ones that were living the longest. And he said, well, if you can find the worst environment that pine trees live in, you will find the oldest pine trees in the world. And it turned out that was true. Up in the White Mountains and in parts of Nevada, they found these trees, which are the bristlecones that live above normal tree line. They live in awful, awful environments. And they space each other out like this, and they are trees that have lasted for almost 5,000 years. I think it's an interesting idea that you actually want your environment to be as awful as possible if you want to be as survivable as possible. And for those of you who have read Ping's book, I think a lot of Ping's great character comes from that adversity. And you also see in companies that have to fight for their existence that they actually are the more robust companies. The other example I wanted to bring up as an idea of resiliency rather than robustness is this. This is the Pantheon in Rome. This is a 140-foot cement dome that has been continuously inhabited and used for almost 2,000 years. That is a 2,000-year-old roof. That is an amazing, amazing thing. Modern concretes basically cannot build this. And they've looked at the concretes, and one of the things that they found is that they used very different sized aggregates throughout this concrete, so that when a crack started to form, and in fact, it has as many cracks as modern concrete does, when those cracks form in the concrete, they don't actually move through the concrete in a linear way. The whole thing is still stitched together, and just its weight keeps settling down, and it stays structurally as a dome. In modern concretes, you'd have linear cracks that move, and the whole thing would fall down. So this idea of finding ways to not just be robust by being more massive and lasting longer that way, by actually failing in a more graceful way. And that's actually one of the things that they say about the bristle cones, is that it's not that they live a really long time, it's that they just take a really long time to die. And that there's always one little string of life that's going up one branch. That's the thing that really lasts a long time. So, as I talk about some of these other examples, I just want to point out some of these things that are really the differences between robustness and resiliency. Basically, robust things are generally the massive and tough. They're built to withstand. They're stable. But the problem is they tend to fail catastrophically, whereas the resilient things really are the flexible, agile things that fail gracefully in a way that you can actually get ahead of their failure, see that it's happening, and possibly fix it. I'm going to go through a few things that have actually lasted on this time scale. One of the ones we were talking about yesterday with Joel, this machine called the Antikythera Device. This one's personally a favorite because it's a clock, it's an astronomical clock, that has lasted in a way for 2,000 years. It was found at the bottom of the Mediterranean off of Antikythera, Greece. And it wasn't until fairly recently when they started doing CAT scans and X-rays that they really found out what it is. And it's actually a very intricate celestial device that can predict eclipses and sun movement. And basically, by being a mechanical object, this is a recreation of it here, by being a mechanical object as opposed to an electronic object, we were able to find it at the bottom of the ocean, reconstruct how it worked, and make a working clock out of it. So it's one of the reasons, for instance, that we are not building an electronic clock, but a mechanical thing. And also, just in general, mechanical things tend to be more impressive at this point. Electronic things, everyone assumes are magic. So yeah, you also want to be, one of the good strategies for lasting a long time is to be lost. And then you need to be found, but you need to be found by the right people. This is one of the Dead Sea Scrolls. Probably many scrolls like it were found at the wrong time by the wrong people and just rewritten over or lost or burned. But these were, it's paper that lasted 2,000 years. And it was in a clay vessel. So it was had the right chemical environment, and it had the right person finding it. The other interesting one, and this is an interesting case in designing in resiliency, it's probably one of the only cases that I know where it was very purposefully done. This is from a tomb in northern China that was exhumed, and when they exhumed it, they didn't quite know what they were digging through until later. And so this is a lacquerware set that's over 2,000 years old again. It looks like it's brand new. You could pretty much eat out of it. But when they looked at how the tomb was built, it was actually built with a layer of dirt, a layer of cedar, 6 feet of activated charcoal, layer of dirt, layer of cedar, and some clay to keep out the water. And that activated charcoal was actually a getter for the oxygen in the tomb. And so they understood 2,000 years ago how to remove the oxygen out of this space, and the contents of the stomach of the person who was exhumed out of here was actually analyzable. So it's one of the only cases I know where an ancient culture really not only tried to preserve, but understood the chemical environment of what they were working against. Another method of having things last is to have a sacrificial layer. In nature, we see it with things like lizards' tails. a kind of curious example that is both an attempt at being massive and robust, but also had a strange resiliency of the pyramids. The basic pyramidness we have really just because of the massiveness of them. They were stripped of their outside casing stones, and the insides of the tombs were taken away. But by taking those things away, we actually kind of feel as though we took the value from those things. But the basic pyramid is still there. Another example of this was the Taj Mahal, which had all kinds of jewels all throughout the halls, which were pried out by the English during the last kind of sacking of the area, but they didn't destroy the building. So this idea of having a high-value sacrificial layer that you can strip away from a thing, and then you actually leave the true value, which was the architecture that was there. Another way that you can make things last for a really long time is to make them extremely remote. And this is more of a robust strategy than a resiliency strategy. Just get out of the way. If you're in a city, basically you're much more likely to get involved in a war or get out of fashion and be torn down. This is a site that I visited a couple winters ago. This is the Seed Vault in Svalbard. This is what the airport looks like as you're approaching the northernmost human settlement in the world. And they have truly found one of the most remote sites in the world. And they also are trying to store all of humanity's, kind of a backup copy of all of humanity's seeds. And they get a naturally chilling environment, which you can see in this picture. And these are the seeds themselves. One of the strange things about this visit to me, though, is actually this book, which really surprised me in that as remote as this place is, I was signing my name behind Ban Ki-moon, Jimmy Carter, these kind of amazing people that the remoteness and the strangeness of this place is actually part of its attraction. And it's what makes it mythic, and it's what makes people tell stories about it. And that's really what we wanted to be able to do with the clock, is change the way people think about time and make a kind of mythic journey that you have to take. So this remoteness really seems to work in that case, both as a preservation strategy as well as a kind of myth-building strategy. Another way to make things last a very long time is to take a very long time to build them. The cathedrals of Europe, this, for instance, is the cathedral in Cologne, Germany, and it took, sort of was finished 600 years after it was begun. But this is a really key one, and it seems that the most dangerous time for anything, and I'm sure you'll also see this in the software industry, is like right after something is built, it goes out of fashion before people really realize its value. And especially in buildings, it's hard to be a UNESCO World Heritage Site when you're just finished. And often it takes having things torn down and destroyed before people realize the value of that in the past. So you want to be able to survive that kind of unfashionability phase and be an antique. And the interesting thing about cathedrals is that they're already an antique by the time that they're done. Another example is Sagrada Familia. It's now, I think it was started in 1885. They think it's just past its 50% completion. It's on about its sixth architect. Gaudi was just one of them. But it is already at 50% completion a UNESCO World Heritage Site. So it seems to be taking a good path. The other one is to really just maintain something. And this is back to the resiliency idea of building an institution that can survive alongside of the object, and in some cases, having the object help that institution survive. So this is a temple in Japan. It's one of the longest-lived, continuously standing wooden structures. So it's made out of very ephemeral materials, wood. And it's in a humid, rainy environment, but it has had an institution surviving alongside it, maintaining it for now, I think, over 1,600 years. It was also one of the tallest wooden structures in the world, completely wooden structures in the world up until pretty recent history. Another Japanese example is one that's actually rebuilt every 20 years in an alternating site. This is a very rare picture here of the temples at Ito, which are generally, there's only one of them there. And in fact, they're now building the set, which are going to be the new ones in 2013, which I'm hoping to go for. But these basically are built out of rice paper, thatch, and wood, and have lasted for almost 2 millennia. Part of making things last in that robust strategy is generally to put them underground and to put them into massive amounts of rock. But I've found that there's been one problem with this strategy, in modern times, in modern efforts, and that is generally water. This picture was the last picture they let me take before taking my camera away. This was at the Mormon Genealogical Archives outside of Salt Lake City, Utah, and they built this in the 60s to store all their genealogical information. They built it basically as a nuclear bunker. But the bottom 4 drawers have flooded in this facility about 5 or 6 times since the 1960s. So, and this becomes a recurring theme. In every underground facility I've been in, they have failed to understand water. They always assume that they can stop the water, and they always fail. What you need to do is the resilient thing, which is to divert the water, not try and stop the water with some kind of robust technology, or hopefully robust technology. This pump system right here was the one that's in the seed vault they had to retrofit only 2 years into its 1,000-year design life. So as I said, underground does turn out to be a great strategy. Most of the things that have survived on this time scale have been underground. This is one of the nuclear waste repositories. Its design life of 100,000 years in Onkalo, Finland. And this is the one here in the United States, which is actually a congressionally mandated 10,000-year project, and then more recently been shut down. I suspect it will be reopened. But the building underground does seem to afford very long time spans in general. And the last example I'll show is to being very careful about ideologies. If you do want something to last for thousands of years, having a strong ideology alongside it can be one of the more dangerous things that you can have. This is a picture of the Buddhas of Bamiyan. You can see a person at the bottom there to give you an idea of the scale. These were in Afghanistan, and they were bombed and used for target practice by the Taliban right before 9/11, basically because they were the wrong idol. And so they became out of fashion, several hundred years after they were created. But as innocuous of a symbol of religion as a Buddha can be, it can still be strong enough that someone would want to take it down. So what are our conclusions from looking at all these things? Basically, we do want to design the clock to be lost and to be found. We want it to kind of take note of the times when it's not being paid attention to as much as the times when it is being paid attention to. We want to make sure that we really think about the chemistry of the environment just so that it doesn't go away in terms of being this everything is burning idea is that basically oxygen is the danger to all things that need to last for a very long time. Everything is burning in terms of oxidization, and we want to make sure that we can avoid that. The sacrificial layer is an interesting question. Should we line a 10,000-year clock hall with high-value things that people could steal and think they have taken the value of it? So far, we haven't designed that in, but it's something we could do. We are using a remote site, and we are actually building it on a fairly fast scale. We're not building it on a multi-generational scale right now, but we aren't done yet, so we'll see how that goes. Designing an institution alongside it, we're trying with the Long Now Foundation. We're only 15 years old now, so we'll see how we do in 10,000 years. And this idea of diversion, we've designed a totally underground site that diverts water all the way through it and doesn't catch water like a lot of these other underground facilities. And the ideology one is an interesting one. We do have an ideology of long-term thinking. So if that could ever be considered threatening to a future culture, we don't know. But hopefully that doesn't put us in danger. So I'm going to talk now about the actual clock project. First, about the site that we're building in West Texas and how I met Ping. The design principles of the clock are basically design principles that are about resiliency, and basically we gauged all other clock devices against these principles, that it had to have, obviously had to last for a very long time. It had to be maintainable with much lower technology than we have now. It has to be transparent so that if you found it and it's not working, you could fix it. It has to evolve so that if we use calendar systems, for instance, we know that calendar systems have not lasted for 10,000 years, so we want to use a calendar system that can, or parts of the calendar system that could be updated. and that we want to be able to build it scalable so that we could start with small things and build our way up, and which we have done. To give you an idea of the type of problem that you have to solve when you're building a 10,000-year mechanical object, there's this problem here, which is the analemma. And you've probably seen this out in the middle of the Pacific Ocean on some of your globes. This is basically a picture of the sun at noon through the course of the year. And why this is a problem for a 10,000-year clock is that our clock, as I said, was designed to be both lost and found. So we want it to be able to keep time when people are not there to maintain it. And one of the ways we do that is to synchronize the clock to the sun on any sunny day. And so there's a little piece of the clock that sticks out at the top of the mountain, allows the sunlight in, it heats up some metal, that metal expands, we get a mechanical trigger that says, this is solar noon. But we also have a pendulum in the clock that's ticking very, very slowly. And that's keeping what we call absolute time. So now we're keeping solar time and absolute time. And that is the difference right there between solar and absolute time. If you drew a line diagonally across all the points of that 8, you have this plus or minus 15-minute difference of solar time to absolute time. So there have been clocks that have had to solve this problem, but they've never had to last for 10,000 years. So you could just have a little mechanical cam that has this, a simple two-dimensional cam that has this difference in it. But the Earth is also slowing its rotational rate by about a second a century, and it's wobbling on its axes every 26,000 years with the precession of the equinoxes. So this cam is a 1 in 10,000 year cam. We have to replace it every 10,000 years. And it turns around once a year and gives us this plus or minus 15-minute difference as it evolves over 10,000 years. Other types of problems are we need to read the year in 5 digits. So we have the decamillennium bug kind of solved early on this one. The this was one of the first prototypes that we finished. This one's at the Science Museum in London now. The other types of problems were actually in pure gearing. This was an orrery prototype that shows the human eye visible planets, but just like that last prototype I showed you, you see these disks that are at the bottom of the device there. And instead of doing calculation with gearing, which is an analog method, and the problem with gears, if you're trying to do very big division, is that every time that gear goes around, it's a little bit of material wears off, and then a little bit of material wears off again, and you have this cumulative error adding up. And if you're trying to be as accurate as we are over 10,000 years, that just doesn't work. So what we have is a binary mechanical computer that does all the big reductions for us. So we have kind of 27-bit numbers that we can divide with, and we can do big reductions with binary mechanics, and then transfer that with, in the last stage with gears, and have the kind of accuracy that we want. So as I said, I'm going to show you some of the stuff about the site. What I'm not really going to show you is a big cutaway thing of the mountain and the clock that we're building within it. There's a few reasons for that. One is it's never a view that you will ever see, so it's kind of a worthless view. And the other one is that a lot of the clock experience underground is we're hoping to be a kind of surprise that you get to discover. So you're not going to see that today, but I'm going to show you little bits about it. I also don't know what it's going to cost, but it costs a lot. The funder of the project is Jeff Bezos of Amazon.com. And I think it's probably worth just saying a little bit about why he, of all people, kind of, in a sense, we might even kind of blame people like him for the accelerating of human culture. Why would somebody of the dot-com era be interested in funding a 10,000-year thing? And he actually is very much a long-term thinker, and if you are an Amazon shareholder, you'll realize that he's been posting his original shareholder letter with every quarterly results, which was that they're building things for 10 years from now, as they work. So they always have been thinking long-term, and he's been an amazing partner to have on this project. The other thing that I don't know is when it's to be done. We're not building it to a deadline. We're hoping to build it correctly, not build it so that it's done on a certain day. project started in 2010 on site.
So I think this is kind of a big day for Danny. It's a big day for all of us, but maybe especially for Danny.
We'll construct everything from that tunnel. So we'll pull up a giant raise bore bit, which will create a shaft all the way to the top. But we can't bring that bit in until we have the tunnel.
I'm a steward for this clock. So anything you're designing to last 10,000 years, you know, it doesn't really belong to anybody. And so I'm kind of the first steward. And so my job is to take care of the clock until it's established and rooted.
3, 2, 1, fire!
Wow!
So that was a very exciting day for all of us. We were 5 years into the design process before we got to blow stuff up. And so, interestingly, some of the processes involved in what looked like a pretty crude thing is that Jeff was using a plunger that was used over 100 years ago, but it was connected to a computer that then computer detonated all those charges so that they detonated in a certain way. And if you're trying to build an underground space to last for a very long time, you have to do things like not overbreak the rock that you're blasting. So the blasting itself becomes a total art. And this is the site. It's in West Texas that we're building at. This is in the Sierra Diablo Range. It's near the Carlsbad Canyons, just south of New Mexico there. You can see this is part of the project already underway. The little white bits at the bottom of that cirque there is actually the material that's been coming out of the blasting. And the very first thing that we had to do was get this whole site into a computer. So we overflew it with LiDAR and started building trails and access to it. And we also had to build some really complex shapes, which the mining industry is not very well adapted to doing. They're really well adapted to moving through underground rock very fast. So this was a blasting plan that was created for building one of the main chambers in the clock. We also had to make a tunnel, a vertical tunnel, all the way through the entire site that was 500 feet tall from that tunnel that we made horizontally. This is a raise bore device that's used usually in mining for making air shafts and elevator shafts and things like that. This was one of the drills was actually in Chile during the rescue of the Chilean miners. And so after only 10 days, it comes out at the top. We have a 500-foot vertical shaft. It was actually right at this time that I contacted Ping. We needed to do a laser scan of this site and get all the geology into a CAD system that would allow us to start doing geology while they were doing all the improvements to the site that would allow us to start getting people and equipment down in.
Okay, we're recording. Go ahead.
So that was actually Penny on the side of the frame there. But she came out and with a great team that allowed us to put very expensive gear on an end of a small rope and dangle it down 500 feet of vertical raise bore. The other fun part of the project, but also the very difficult part, is that we're trying to use very crude technology to do very nuanced shapes and nuanced design. And so, as I said, that was that blasting. I showed you that blasting plan, and here's that chamber. Every single one of these holes that gets drilled and loaded with high explosive, both the hole depth and the amount of high explosive, very carefully thought through, so that we ended up with exactly the right shape. And we used some amazing folks who build wine caves, it turns out. We started with a mining company and had to move away from the mining companies and move towards the people who build wine caves so that we could build things that were actually aesthetically beautiful. But basically, to build that kind of funny-shaped room, we had to deck it down layer by layer with high explosives. And this was one of the bottommost layers here. And then laser scan it. Kind of looks like a brain, strangely. But this all came out to within about 6 inches of the design, which was pretty amazing. given that we were using explosives. The other part of the project that we needed to do is move people through it, right? So we have this 500-foot vertical raised bore that we want to put all the clock mechanism in, but we also now had to cut a staircase in it. And we also wanted to taper that entire raised bore, and we wanted to taper the staircase. We wanted to make it very kind of interesting three-dimensional environment that people move through. And unfortunately, there's basically no technology in mining that could help us. We went to Carrara, Italy, and borrowed one of the technologies that they use. They mine marble, but they're trying to mine marble to get blocks out from underground. We wanted to make the negative space. So we took one of their saws. They've developed these really cool diamond saws that have blades as long as 20 feet, like chainsaws. And we borrowed that and then turned it into a 27,000-pound robot that we could dangle down this, this raised bore. And it also has to be able to brace itself. So we working with KUKA Robotics, we were able to do this. And in fact, the software that programs this saw is all done as a Grasshopper add-on with McNeil's software. So the idea was this saw that could make horizontal cuts, and you break the plates out between them, and you make 300 vertical feet of stairs. And just recently, this video is actually just from a few weeks ago, we just finished one of the phases, which was the part where we were tapering out of this whole underground space. So this has got a 9-foot diamond chainsaw blade on it, and it can cut rock pretty much like wood. Pretty amazing. And it has a repeatability of about 0.005 of an inch. It has a vertical rise of over 500 feet and a working envelope of 36 feet. So it may be one of the largest high accuracy robots in the world in terms of working envelope. The final space that it created is pretty interesting, and this is also one of the tests of breaking out the plates for the stairs themselves. And that's what the finished staircase looks like. The entire thing is tapered from bottom to top, so it'll be 5 feet wide stairs at the bottom and 3 feet wide stairs at the top. So every single cut that this saw makes is different all the way throughout. It's been cutting now for 3 months, and it's probably going to be cutting for another year, finishing these stairs. We just got back these photos from the lower flared out section. There's about 75 feet of cutting to flare out the 12-foot raised bore out to 18 feet. So that's the site. And I'm going to show you a bit of the machinery that's underway. As I said, we've had to solve some of these problems of rectifying kind of 10,000-year things to near-term things. We also had to solve a lot of problems about material science to test things to last for this long. A lot of you, I'm sure, are engineers, and you're all wondering, what are the bearings in a 10,000-year clock? And I'll show you those. We kind of got lucky in this project in the development of satellite bearings that have become very cheap. I'm going to show you a couple devices. One is parts of the Chime Generator, which is a device that can ring a series of 10 bells in a different sequence each day for 10,000 years, and parts of the power system. These are both parts that we're just now finishing at full scale. This is one of the largest gears in the clock, all made in 316 marine grade stainless steel. All the teeth of those gears are actually three-dimensionally curved, so that the pinion, which he's actually holding in his hand there, as it rolls across, there's never a time when there's sliding friction. It's always rolling friction. The bearings, as I mentioned, come really from the satellite industry. They're unlubricated ceramic bearings, so ceramic balls on ceramic races, and they provide two interesting things for us. One is that if there's two slightly different metals, let's say titanium shaft with a stainless steel outside casing, they provide an insulation of galvanic corrosion, which is that if you've ever seen a penny sitting in the bottom of an aluminum boat in salt water, it can pretty much just corrode right through it in a matter of months. That same effect would be taking place much slower over dissimilar metals in our clock. And these bearings, since they're separating all the shafts from the outer casings, basically solve that, as well as operate with no lubrication. So they're not attracting dirt, and they don't run out of lubrication for that reason. As I said, one of the first things that we're working on is this Chime Generator. This was the small-scale version, which had Geneva wheels that made the mechanical computer that rung a series of bells in over 3.5 million combinations. These were 12-inch cams in this one, and now we're working with these where we built our own ceramic bearings for these, and these are 8 feet in diameter and all stainless and titanium. There's going to be 20 of these modules strung through that whole vertical raise bore. And one of the last bits of the clock that I have to show is the part that just recently got finished, which is the power system. So these are parts that are in testing right now in our space in San Rafael. The power system has a 10,000-pound weight that's hung on a huge rack gear, and as that weight falls, it drives this huge differential. It's all stainless, titanium, and ceramic. And that's the storage for the power, and people come and wind it. The idea of the clock is that the clock can keep time all by itself with nobody there, but for all the dials and the chimes and all the parts of the clock that you see, you have to wind it. So the clock is quietly keeping track of time just from the temperature difference from day to night from that same device that gives us our solar synchronization. It's also winding the clock just enough to keep it ticking, but for you to see that time, you have to wind it. And so these are some of the very first tests of that whole mechanism. And to finish, I just want to tell one last story that will hopefully bring a little bit of relevance to what you've just heard. And it's a reminder that basically a 10,000-year event happens every day. We were just reminded of this again, maybe more like a 1,000-year event or a 100-year event that happened with the meteor impacts in Russia. But in Japan, in the 2011 earthquake, that was considered a once-in-10,000-year event. The tsunami that came after it was considered a once-in-every-few-hundred-year event. But that once-in-10,000-year event became extremely relevant to the daily lives of a lot of people. And we often ignore those large cycles to our own peril. Most interestingly, it came out of that story was these little markers. And these markers are found throughout Japan. And this one read, "High dwellings are the peace and harmony of our descendants. Remember the calamity of the great tsunamis. Do not build homes below this point." This was 400 years old. It was a reminder from the last tsunami that was that big. And it was completely ignored. And people thought they could build giant, robust seawalls. They thought they could solve the problem with new technology, with a lot of mass and a lot of hubris. And those seawalls were overwhelmed. And this little village of 40 people that basically went with the resilient principle was saved, and we're fine. Thank you very much.
So we'll have questions. Can I have my mic runners?
Zander, thank you. Fabulous presentation. Wondering if you have, or how you have thought or speculated about your team versus teams thousands of years ago. You know, who are the guys sitting around thinking about the aggregate mix in the Pantheon, or who are the Jeff Bezos or sponsors for the pyramids or something? You know, what did their team look like, and what does your team look like in comparison?
That's a really interesting question. You know, what did teams look like that built the pyramids and some of these other great structures? I'm just now learning a lot more about Roman concrete. There's a woman in Berkeley who's been lucky enough to get cores of several of these things. There's just now really learning some of the understandings that they had about the chemistry. And a lot of the archaeologists have really thought it was an accident because they happened to be close to volcanoes in Rome that had what's called pozzolanic material that was really long-lasting chemically. But she's really finding that it was not an accident at all. They knew how long-lasting this material was. They, in fact, exported it from Rome all around the Mediterranean to use it. And as you go up in that dome, the mixture changes. And that it cured over that. You know, we use modern accelerators to to make that accelerate, and they waited a whole year for that to cure, most likely. So they were extremely aware of it. What's curious about it, and what's also curious about that Antikythera device is that we don't know much about the leading up to it. It's hard to, basically the things that failed are gone. So it's hard to know a lot of their process, and they didn't record a lot of their process. The thing that's always curious to me about thinking of some of these ancient teams is, people say, the aliens built the pyramids because there's no way ancient people could do it. But, there's been these great shows on the Discovery Channel that show, okay, well, you could actually do it with old technology. But in every single case of those reconstructions, the thing that they really realize is how just difficult it was to organize everybody. And project management, like in the world where there's no telephone to call someone, there's no alarm clocks to wake them up, there's no radios to, for the 500 feet apart that people were who were working on the pyramids from corner to corner. How did they organize that project? And that's the stuff that's just kind of lost to dust. And we really don't know. And so I spend a lot of time wondering how they do it, because I do it by email and cell phones and lots of software. But I'm always curious as to how they kept everyone on task. I think in not all cases they were doing it for reasons of longevity for society. Things like the pyramids were built really because someone wanted their afterlife to go on for a very long time and could afford to fund it. And I think that's very different than our project, in that Jeff is really, as you saw from his comments, he doesn't really feel that anybody owns something that's going to last for this amount of time. And he's not asked for any naming on anything. And so I think most of those motivations are kind of different.
Some years ago, I learned that you were using Pro-E for designing this clock. And I was kind of curious, anybody from PTC, did you provide Long Now with a perpetual software license? But seriously, this kind of project brings up a couple of interesting issues with software, one of which is long-term access to your data. Maybe it's not important that you have access after the clock has started, but it's been a long design project. But the other is that technology has improved over time, and this seems like would be an excellent example of a project to use systems modeling or systems engineering. Have you actually stepped up and used those kind of technologies in the design of the clock?
Yeah, so it's a very interesting question. We've been lucky enough to have all kinds of fantastic software sponsors. As I mentioned, McNeil worked with us for the Rhino and the Grasshopper to program that saw. Most recently, Autodesk has really stepped up, and most of the stuff that you've used, that entire power system was designed in Inventor. And the earliest software sponsor was PTC. We did a lot of modeling in that, and we continue to do so. So we really just have we basically try and give our engineers whatever they want to use. We've been very fortunate to have great partners that helped us do that. The challenges that you mentioned are very real. The very first prototype that we built of that mechanical computer was built in AutoCAD that was basically kind of a 2.5D project. And that was in 1997 and through 1999. And we were almost going to do it in 3D. And we went, well, let's do it in 2D because most of the parts are 2D. And now we have these kind of legacy models moving forward. And I'm sure a lot of you probably know more about this problem than I do. What we've done is always made sure to publish everything in actual paper and in more open formats than the proprietary software would want. So we always publish in PDFs and DXFs, and now we're all of our 3D models. We always save out a step file of everything that we do because we assume that the software that we're using is going to expire, or the version is not going to work in a way that's going to be referenceable in the future. Now we lose all kinds of data, obviously, by moving over to these non-proprietary formats, but we want to at least capture the basics of what it is. But I'm very interested in this topic, and we try and actively archive as we go. We use tools that remember all our version history, but all those tools are also they're proprietary and have dating, and will go out of date too. So I'm very interested in that conversation. Our fallback is literally printing things out in paper.
Bob?
Thank you, Brad. I was wondering how and why the site in West Texas was chosen, and I take it remoteness was a big consideration?
Yeah, so the site in West Texas was chosen for a few reasons. As I mentioned, we actually purchased the site in eastern Nevada, and that was that picture that bristlecone came from. And we thought we were going to build there. It's in holding in the Great Basin National Park, so it has an advantage of kind of having some near-term government protection around it. It has the disadvantage of having near-term government protection around it, in that they are very particular about access and all these things. So it looked like that was probably, we were going to spend the next 10 years permitting and figuring out how to do it. It's also much higher. It was another 5,000 feet vertically, which is a lot more of a challenge when the oxygen gets that thin to work. And then Jeff had this property in West Texas that had the same limestone composition. It was entirely private. You could drive to the top of it and from a different access, and even though we're building trails that people visit from below by hiking. So it really just won out because of that. But and the other advantage is it's even more geologically stable. As you may know, Nevada's not very geologically stable. As you get as far east as we were, it's better. But we're designing against a 6.0 earthquake, which is our geologists tell us is about 10% chance to happen in the next 10,000 years.
Okay. Dave?
The examples you give in Japan and many of them are fundamentally parasitic on living systems. In fact, to persist, you have to have someone there to maintain it, you have to have someone there to build the new thing, and so on. And that will be true to a degree for your clock as well, at least to crank the main mechanism and so on. And I wonder if perhaps it would be at least as good, if not better, a symbol if you had built a living system rather than a mechanical one.
Yes, there's many ways to build a 10,000-year clock, it turns out. And we've invited other people to do it, and some of those concepts are on our website. And people, in fact, some of the ideas were planting a bristlecone forest, effectively kind of in rows so that it grew up in this kind of ramp. Part of what we're doing literally is theater, right? Like we want to engage people and we want people to tell the stories. So far we've been lucky. Neil Stephenson, who, if you know him as an author, wrote a New York Times best-selling science fiction book that used the clock as kind of the central metaphor of the world. So it was at least the beginnings of our myth, hopefully. So part of it is really just choose the way that you think is going to be the most engaging to people. This big thing ticking away under a mountain was really a part of it. But I do think it's very interesting that you say about the parasitic. I would actually say symbiotic. I think that Shinto religion has survived through the onslaught of kind of Buddhism and other religions that have come through Japan, where it's kind of the sub-religion of all the other ones. And I suspect that building of that temple once every 20 years, where a master teaches an apprentice, 20 years is basically a generation, not only helped them maintain that building, but I suspect it also helped them maintain that religion of kind of that physicality, reminding them of why they're there. So.
I've got something a little more pedestrian for a question. You talk about storing the data for how you built this clock, and you mentioned making it transparent so they could look at it to reverse engineer it. Did you think about printing the instructions right on the parts?
Yeah, so we have another project, which I didn't mention, but it's called the Rosetta Project, where we've been working on that particular problem. And again, it's an extremely analog solution. I think it's very likely that we are going to print some kind of instructions either in the parts themselves of some of them, and as well as the rock that they're embedded near. What's funny about instructions, and if you've ever put together an IKEA bookcase, you will realize this, is that ideograms are very difficult to translate over time. They're actually vastly more difficult to translate than text and phonetic alphabets. And the Rosetta Stone is a very good example of that, where the hieroglyphics are vastly more difficult, as well as Mayan glyphs are vastly more difficult to understand than a phonetic alphabet. And that's because they're idea-based, right? So there's a little hieroglyph of a piece of wheat. And what that piece of wheat meant to the people in ancient Egypt is obviously very different than what it meant to us. But we used a gallium ion milling machine that normally cuts circuitry into chips, but instead of cutting circuitry, we cut words. And we collected over 2,000 examples of linguistic material of 2,000 languages from around the world over a decade. It was a National Science Foundation funded project, and micro-etched it into this disk that can last, that it's into silicon, and then you cast that into nickel, and that can last for several thousand years. So basically, that was the library side that Stuart was interested in, of how you store information for a culture. So we were looking at it a little bit more broadly as not just the manual for the clock, but also the manual for civilization. How do you store information, especially as we increasingly are putting our entire cultural record into digital means that, as many of you probably know, has basically no forward migration path. If you've ever tried to open up a Word 2 document. I know we have some people from Microsoft. I would love to see a Word 2 document. So far, no one has answered that challenge from Microsoft that I've seen. But there's been some great backward compatibility tools that have been built. But who knows if the Shakespeare of our time could have been writing in Word 2, and that's it, right? We lose it.
So, well, can I have a round of applause for Zander?